Over the years in algebra, we've learned a lot of formulas and graphing things for 2 dimensions. And now we want to see how that compares to the 3rd dimension, right? When we add in these 3 dimensions, what are the analogs? Now, some of them are going to be pretty obvious, and some of them are going to be a little trickier. Okay, so let's first start off with the distance formula, which should look very familiar to us. We've actually already used it for a particular formula that we've run into already in section 13.1. So we have 0.1 over here, and we have 0.2 over here, right? So the distance is, now think about this, there's a triangle, right? A right triangle. And so the distance is the square root of, now the horizontal piece is the difference in the x's, right? It is x2 minus x1. And the vertical is y2 minus y1. And so therefore, when we want to find the distance, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. The Pythagorean theorem, right? Now, when you're in 3 dimensions, if you have 0.1 and 0.2, it doesn't really matter where they are. Boop. It's the same thing. It's just with a 3rd dimension. So because the points have 3 components, you'll have to take x2 minus x1, y2 minus y1, and square it, and then z2 minus z1 and square it. There, my z looks a little strange, so I fixed it. All right, that's easy enough. Now, what if we have a point and another point, right, 0.1 and 0.2, and we want to find the midpoint, right, the halfway spot? Okay, well, the midpoint is a point unto itself, right? It has its own x and y coordinate. The x coordinate would be the average of the 2 x components, and the y coordinate would be the average of the 2 y components. Easy as that, right? X and y. When it's in 3 dimensions, 0.2 over here, 0.1 over here, or vice versa, it doesn't really make any difference. And the midpoint is in the middle, which for some reason I always draw along one of these coordinate axes, but it's not. It just looks like it is. All right, so that midpoint would have 3 components, right? It's going to have the average of the x's, the average of the y's, and then the average of the z's, right? The mean of the z's. There you go. All right, now, when we drew x equals c in algebra class, we learned that that was a vertical line, right? So it's a line. It goes through a particular x value. So, I can pick an x value, like x equals 3, and I can say, okay, that's a vertical line that goes through. So I drew x equals 3 as an example, but it's a vertical line that's parallel to the y-axis. Okay, so if I did x equals 3 here, well, I might do more than 3. 1, 2, 4, 5. I'll do 5. All right, it's not going to be a line. It's going to be this whole plane that cuts through at x equals 5. And then, let me just put dots all around it. It's parallel to the YZ plane, which is the back over here. So it's a vertical plane. Well, not really vertical, because there's no, in 3 dimensions, what's up is down. There's no way you can guarantee. And it goes on forever as well, so it's not really quite like that. But it's a plane that's parallel to the YZ plane. And the reason verticality shifts is that, remember, you can shift where particular axis point. So for example, in this particular drawing, z is actually back here. So x equals a number would actually be a horizontal plane in this iteration, because you can twist and turn the axes around to suit your needs. So I'm just going to say that it's a plane parallel to the YZ plane. All right, so now what about y equals c? Well, we learned that y equals c is a horizontal line, right? So it's a horizontal line. I'll draw y equals -4, just as an example. Oh, and I should have said this is x equals 5 that I'm drawing right here, if you want to see that. All right, so y equals -4. This is a horizontal line because in 2 dimensions we definitely know which one's up and which one's down. So parallel to the x-axis. Okay, now if I do y equals 5 here, I would have this plane right here, and it goes like this. Maybe I should go a little bit more. It's like a door on its hinge. And it's a plane that's parallel, I got 3 L's in there, parallel to the XZ plane. There's this plane over here with the Z axis and the X axis, and it's parallel to that XZ plane. Now Z equals C, of course, doesn't exist unless you change your coordinate axes to be X and Z, or for example. So, but for these ones, oh, and this was y equals 5 that I drew, and then this will be z equals 5. Z equals 5, I think, is the easiest because it looks like a flying carpet. Like that. So this is z equals 5. So this is a plane that's parallel to the xy plane, which is down here. Okay, so now what about spheres and circles and all of that? Okay, so in 2 dimensions, we have circles. So let's see if I can draw this well. I'm not the best circle drawer in the world. I was doing okay there until quadrant 4 got me. There we go. All right, so that's a circle, or an attempted circle. So this is a circle. Its radius is, I think I drew 3, and it's centered at the origin. Now, there are a couple ways we can draw formulas or write formulas for those. So let me just write those down. When you're centered at the origin, then it's easier. It's x squared plus y squared equals r squared. We learned that in algebra class. And then we also have learned that it's r cosine theta, r sine of theta, right, in a parametric / polar form that we learned in Calc 2. So I'm just going to write a big or. Okay, so then what if it's not at the origin? Well, then there are formulas for that as well. So if it's not at the origin, if your center is the point HK, then it would be x minus h squared plus y minus k squared equals r squared, or r cosine theta plus h, r sine theta plus k, right, in parametric form or polar form. Okay, so how do we expand this for 3 dimensions? So how do we work with a sphere with radius 3? Actually, I think I'll draw radius 3. Yeah, I'll do radius 3. And the center is the origin. And the answer is you kind of draw it the same way. You start with 1, 2, 3, 1, 2, 3, 1, 2, 3. So I kind of hit my axes here. And I worry about the YZ axis first, because that's kind of straight up and down. And then I give them a little tummy, a little belt. And there we go. Now I've drawn a sphere. I took a circle and I added this perspective to it, and that made it a sphere. Now the formula, when it's centered at the origin, is similarly easy. It's x squared plus y squared plus z squared equals r squared. There are polar equivalents to these, but we're not going to get to them until much later because they're trickier. So we'll work on those. There's two different coordinate systems we can define this as, in the spherical or the cylindrical coordinate systems. So there are different coordinate systems. So right now there's no equivalent to this polar form. So this is polar and this is rectangular. And right now there's no three-dimensional polar yet, but it's coming. There will be one, but there's actually two of them. So there's two polar forms in 3 dimensions, which are called cylindrical or spherical, but we don't know them yet. So we're just going to hold off. Now, if the center is HK, it'll be HKJ, for example. Then it would be x minus h squared plus y minus k squared plus z minus j squared equals r squared. And again, there is no polar equivalent as of yet. There actually is one, but it's more complicated, so we're not going to explain it right now, but it's coming. Wait till a couple chapters from now.